Good afternoon and welcome to our Agrivoltaic presentation. We are Senior Design Team 23123. Here's a brief overview of our table of contents. We're going through the introduction, methods and materials, results, and conclusion. The goal of the specific agrivoltaic project was to mobilize solar panels by placing them on a trailer. The solar panels will be able to shade a water tank, which we use for irrigation, and the water tank will help cool the panels, which will help the overall efficiency of the system. The overarching goal of this project is to have solar power, grazing animals, and crops coexist to maximize land usage. This sustainability project is on a small scale, but can be scaled up for larger industrial farms. Foreign institutes and governments continue to push for investing in new sources of energy and cleaner agricultural practices in order to best adapt to persistent climate challenges. Certain criteria that we selected for our project was the adaptability, infrastructure costs, and weather restrictions. Key project constraints include providing enough shade and water for surrounding crops and sheep, must be transportable on a road, and must be connectable to the farm's power grid. Why is this important? The UN Food and Agricultural Organization has warned that 90% of the Earth's topsoil can be eroded by 2050. As impacts of global warming continue to provide humanity with complex issues such as food security or water availability, there are new avenues to find these solutions, such as overcoming land scarcity by combining solar farming methods and agricultural practices, minimizing the temperature of the solar panels of the system and maximizing solar energy output, and optimizing panel shading and crop growth. With agrivoltaics, there's a decrease in land competition for the production of food and energy. Potential benefits include opportunity for increased job growth, an increase in energy output for communities potentially disconnected from standard energy sources, a decrease in overall water usage, and decrease in total carbon emission.
From these criteria and constraints, different types of software were used to build a 3D model as well as a physical prototype. Arduino was used to code the solar panels and motors used in this prototype. Excel was used for calculating the energy produced by the solar panels, as well as the evapotranspiration rate of our plants beneath our system. And SolidWorks was used to make our model, which will be shown on our next page. From this trailer, you can see our total system with 2 water tanks that will be used as water storage for sheep and other grazing animals. The side view better helps show our structural system that will be holding up the 12 monocrystalline solar panels that are connected in series. You can also see a central bar that our panels will be resting on. On there, a motor will help with rotating the panels on a central pivot point for solar tracking. This SolidWorks model is meant to represent an 8-foot by 18-foot by 14-foot full-scale product. For our prototype, we have 2 monocrystalline 3-volt panels that are connected using gauge wire. For the motor, we used a 1.5 watt DC motor to power the turning mechanisms. For the solar tracking aspect, we programmed with past solar data from the NOAA. We thought this would be the most reliable way to involve solar tracking, since the compass will move with the solar panel's positioning regardless of cloud coverage, direct sunlight, and inclement weather. For the trailer aspect, we used a plywood dolly with wheels. And finally, for the post and rotating bar, we used galvanized steel beams. The prototype is 10 inches by 20 inches and stands roughly 2 feet in the air, and was made by consulting with mechanical, electrical, and civil engineering seniors.
Energy from sunlight is absorbed by the PV cells in the panels. This energy from the solar panels is passed to the charge controller to then be safely and efficiently sent to the battery. The charge controller is used to keep the battery from overcharging by regulating the voltage and current coming from the solar panel. The battery powers the motor through direct current. The battery also powers the digital compass. The digital compass orients the system. The anemometer tracks wind speed, and there are various sensors that track temperature, voltage, and light intensity. The tracking control takes our program code as well as the information from the digital compass, the anemometer, and the sensors to give to the PID controller. The PID controller receives the output from the tracking control. The PID controller can regulate the solar panel's output voltage and current. The PID controller then sends signals to the motors that adjust the solar panels to the most efficient position. Evapotranspiration is the combined process of water evaporation from the soil and transpiration of water from plants, which in our case is tomatoes. As tomatoes undergo evapotranspiration, they release water vapor into the surrounding air, which helps to cool the temperature of the solar panels. This relationship increases the efficiency of the solar panels, and the tomato plants could benefit from the increased moisture levels and the partial shading provided by the solar panels. Our calculations show that the summer months of June, July, and August have the highest rate of water evaporated, making this the more efficient time for our agrivoltaic system. We decided to use solar radiation data to track the sun's position rather than using photoresistors. Photoresistors detect changes in the amount of light falling on a solar panel, which is used to adjust the position of the solar panel to maximize the amount of energy it generates. However, if there is shade on the solar panels or if it's an overcast day, the photoresistors are no longer affected because photoresistors are only able to detect the light that falls directly on them. Solar radiation data is a solution to this problem because it provides information about the position and the intensity of the sunlight that is reaching the solar panel. Our system is now designed and optimized for our specific location and weather conditions to ensure that the panels operate efficiently even when there is shade or low light conditions. Our main costs come from equipment, labor for construction, and maintenance. Equipment cost ranges from about $16,000 to $23,000 to fully build our system. When paying our workers $30 to $40 an hour and including benefits, labor costs about $19,000. The yearly maintenance of our design will cost about $1,600, assuming 45 hours of labor per year is needed to maintain the system. Our overall cost to fully build and maintain our model ranges from about $42,000 to $48,000.
Although electricity is being produced from the solar panel system, it is not substantial enough to sell back and make a profit. However, there are more well-rounded benefits to Awareness Ranch and other farmers who choose to build the system, such as access to shade and water for livestock during the summer months, as well as reducing water usage and increasing crop yield. Plants in an agrivoltaic system benefit in two ways. The soil will retain more moisture over time with the solar panel shading, and plants will have a reduced evapotranspiration rate. An example where water savings can make a real impact to one's farm is through the cherry tomato plant. Based on Arizona's medium to fine textured soil conditions, 2,000 gallons of water would have to be used per day. This equates to $1,500 in water for the 5-month growing season. With an agrivoltaic system, soil moisture was 15% greater when irrigated every 2 days. Less water would then be needed and saving the farmer around $225. Additionally, water use efficiency increased by 65% in tomatoes, leading to less water loss to evapotranspiration. For certain crops, plant yields can also increase greatly in an agrivoltaic system. Going back to the example for cherry tomatoes, fruit production doubled. Tomatoes are especially very heat sensitive in the summer. If temperatures go below 55 degrees Fahrenheit or above 90 degrees, the plant will abort the fruiting process and no tomatoes will be produced. There is even a problem once the fruit do sprout, as they can be easily wrinkled in high heat. Agrivoltaics works well for this plant as it alleviates multiple stress interactions from heat and atmospheric drought, as well as increasing the growing season.
Overall, this agrivoltaic system is able to produce clean energy and facilitate the growth of crops through evapotranspiration. The system has a neutralistic effect by reducing the temperature of the panels whilst reducing water loss for plants and increasing the production yield. This agrivoltaic system is beneficial to combining multiple uses for the same plot of land and increasing its land equivalent ratio by providing two outcomes: solar energy and food production.
Going into this project, the underlying goal was to design a system that could be implemented at the Team Mentors Farm Awareness Ranch. Based on the needs of the mentors, there was an agreement including some unique features that would allow it to stand out compared to other agriculture systems. Future goals for this project are to build a full-size model and include a self-moving feature and battery storage.
The next group that would continue with this project, we recommend implementing a controller that will detect high winds through an anemometer and then signal a motor to make the panels flat against the pivot bar. This would lower the wind drag and further preserve the integrity of the entire system and lessen its need for repairs. Thank you for giving us this opportunity to share with you a little bit about our agrivoltaic system. We can't wait to see you guys at Design Day.